Welcome to this episode of Datadog On. Today we're going to be talking about Rust and in particular how we're adopting it internally at Datadog. I'm Scott. I'm part of the advocacy team focused on application development, and with me today I have Toby and Duarte. Toby, would you like to introduce yourself briefly?
Yeah, my name's Toby. I'm one of the software engineers on the agent metrics pipeline team, which deals with basically all things metrics in the Datadog agent, ingesting them, shipping them out to the Datadog platform, and basically getting your data to where it needs to go.
Thank you very much. And Duarte?
Yeah, my name is Duarte. I'm an engineer in the metrics platform. I'm specifically working on storage for the latest 24 hours of data.
Cool. Thank you. And all of these episodes are streamed and then are made available on datadogon.datadoghq.com. So be sure to check out the previous episodes on there. There's quite a lot of interesting things to go through. By the time you're watching this, you may be joining us live on YouTube Premiere. And if you are, you can jump into the chat. We'll be around to answer questions. We've actually been here before. 3 years ago in 2022, Duarte and one of our other colleagues talked about our initial experience adopting Rust here. We won't cover all of that content again now. We'll try and focus on some different things. If you would like to see it, it's in the playlist on our YouTube channel. But Duarte, could you give us a quick summary of what you spoke about back then?
Sure, yeah. So 2 years ago, we talked a little bit about Rust. We talked about what makes it a unique language. And then we talked about the service I was working on at the time, which we'll revisit a bit later. And that was the very first production service written in Rust at Datadog. Then we also talked about Vector, which Datadog had recently acquired, which is a tool for building observability pipelines on which Toby worked. And yeah, since then, Rust adoption has grown quite a lot.
I'm quite excited to hear what you have both been up to since then. Briefly to us, if you don't know much about Datadog, we're a monitoring and analytics platform that helps companies improve observability and security of their infrastructure and applications. To give you an idea of our scale, we have over 27,000 customers, we monitor millions of hosts, and we capture tens of trillions of data points a day. And this is interesting because that scale actually drives a lot of our interest in programming languages like Rust, and in particular for today, how we are adopting it internally. That's all I've got to say about Datadog. Let's get jumped into the topic. But before we talk about Rust, it's important to understand what our language landscape here looks like otherwise. And as I understand it, we are primarily a Golang shop. Otherwise, could you tell us a little bit about that?
Yeah, that's right. In the very beginning, there was Python, but soon after, the company settled on using Go, particularly for backend services. And it has been that way for quite a few years. Go is a simple and efficient language that has served us well. Most backend services are written in Go. Go is the language that has the most number of internal libraries and tooling. So it's currently the golden path.
Cool. So with that, let's move on to how we see Rust fitting into our local ecosystem. And Duarte, can you give me a bit of a high-level overview of the metrics subsystem?
Sure. So the metrics platform is a highly massive multi-tenant system. It ingests billions of events from millions of hosts per second. And going from left to right, the services on the left receive those that data from customers. The data gets processed and enriched and then routed to storage systems, of which there are two. There's a pipeline dedicated to long-term metric storage, serving primarily analytical queries. And then on the bottom, there's the real-time metric storage pipeline. That one is divided into two databases. The one on the top is the database responsible for indexing all of the tags associated with the point. And this one was a service that we talked about 2 years ago. And then down below, we have the database that is responsible for storing the actual time series values and timestamps. that one was the second production service at Datadog within in Rust. Then on the right, we have the set of services that query and read the data that is stored. And if you're wondering why we have two storage pipelines, that's because most queries, be it monitor queries or dashboard queries, they're predominantly querying the very leading edge of data, because our customers are interested in how the systems that they are monitoring are doing in this very moment. So we optimize for that leading edge. And yeah, over time, queries have become more sophisticated, either because we've added features or we are now servicing new use cases like AI. And that query sophistication, coupled with the ingestion volumes, which ever only go up, drive the scale of the platform. And that scale prompts us to periodically evolve our services. And adopting Rust is part of that evolution. So in the metrics platform, we've adopted Rust quite a lot. All of the storage services are using it. We are now in the process of rewriting the ingestion services to use Rust, and there is appetite to adopt it in the query side as well.
Cool, and I can see Ferris the Rust crab is slowly absorbing the services on the diagram, which is great to see. Can you give me a bit of an idea of the scale involved? Like, how much data are we talking about pushing through the system?
Yeah, for ingestion, we're talking about billions of points, which are time series values coming in from millions of hosts. And for queries, we're talking about many thousands of queries per second.
It's quite substantial. Cool. So we have these things that need to be fast and efficient, and they get more and more complicated over time. This seems like a good starting point to discuss Rust. How did we end up in this situation? How did we decide that this was the obvious next step, moving on from the Golang services that I gather preceded this?
Yeah. So when it came to adopting Rust, performance has been the deciding factor. It is a very objective measure. We had cases of services taking nearly 30% of CPU resources to do garbage collection. And we were also at a point where implementing performance optimizations was becoming more and more complex. So by adopting Rust, we can write very simple and idiomatic code that is very performant out of the box. There's no runtime that we have to work around by writing off-heap data structures and stuff like that. And even if the Rust code is only, let's say, 10% more efficient, at our scale, that is already worth the investment, because even if we gain a very small percentage of increase in resource efficiency, that will translate to a large dollar number in terms of infrastructure cost savings year after year. As we evolved the services, we didn't change only the language, we've also changed the data model and the design. So it's hard to attribute exactly how much we've gained to the language itself. But we have done quite a few apples to apples comparisons over time, be that taking the HOTS function in the Go service and writing it in Rust and seeing how much improvement we get. But also we've implemented POCs in two languages in Go and Rust, almost line by line, translated line by line. And then we saw that the Rust version was much more performant. And then finally, having a language like Rust without a runtime means that we have much more control over the system. So that lets us choose architectures that are a better fit for our data.
Cool. And I think that's an excellent transition here. When you talk about architectures that are kind of in particularly enabled by Rust, what exactly do you mean there? What can we do now that we couldn't easily do with Go?
Yeah, one such example are thread per core architectures, where data gets partitioned across a set of threads, and each partition is exclusively accessed by the owning thread. So like I mentioned, our platform is highly multi-tenant, which means that we could, in theory, partition data by tenant, but then each tenant sends data for many metrics, and each metric has many time series. So we have various levels at which we can partition data. We typically choose the most fine-grained one, which is partitioned by time series. So in this diagram, we have the architecture that most of our database systems follow. Here we are consuming data from a set of Kafka partitions on the left. And then we have a set of cores, set of threads, hosting a multi-threaded Tokyo runtime. And on that runtime, we schedule intake tasks, which are fungible tasks that read data from Kafka, lightly process it, and then route it to the thread that ultimately will own the subset of the data. Each of the storage threads run an independent storage engine. In this case, they are LSM storage engines, so they run multiple workflows. Aside from writes and reads, we have background tasks like compaction and flushing. So all of that is running as top-level features within a single-threaded Tokyo runtime, hosted by that particular thread pinned to CPU core. And we follow a cooperative concurrency model where we try to schedule the CPU according to the current circumstances of the system. And the advantage that we get by doing this is that within each partition, we can access data without taking any locks, without doing any synchronization, and without incurring in cache coherency costs, for example. So it's a very efficient architecture for our data. There's a blog post there with more information on this.
And I gather that this really explicit level of structuring the concurrency with the thread affinity and the lockless kind of style that you just described, this is something that we couldn't kind of ergonomically achieve with Golang.
Yeah, that's right. We need a higher degree of control over the system that Go doesn't really afford us.
So it's a performance monster to put a line under it. Have you seen any other advantages to Rust that are worth discussing?
Yeah. I love Rust. I love how expressive the language is. I love to program in it. I love how the ecosystem is so large and robust. We rely heavily on things like Tokyo and Data Fusion. But my favorite aspect is the safety and correctness properties. I know that if I write a program in Rust, in the absence of unsafe Rust, that it won't crash in production due to seg faults, or that there won't be any data races that will corrupt the results of my queries. And that lets me sleep better at night, literally because I won't get paged for those problems. So I think those are unique properties to Rust among the more mainstream languages. And they're by far my favorite aspect of the language. The trade-off people will say is that we'll be front-loading those costs, those correctness costs, by dealing with a compiler that's much more strict than the compilers of other languages. And indeed, that's the argument against Rust, that it's a very complex language and hard to learn. But I have to say that hasn't been my experience at all. Like newcomers to my teams, even interns, are able to very quickly pick up the language and make production changes within the first couple of weeks. I have to say that async Rust is kind of an exception. There's a lot of implicit behavior there, and the standard library isn't quite where I would like it to be. So that's takes a bit longer to proc. But aside from that, I think Rust is a great general purpose language. I hope that at Datadog it becomes part of the Golden Path, and that it can be adopted by services that don't have any performance requirements, but that will run these correctness properties nonetheless.
Cool. And I hate to put you on the spot, but I know that you were on call this week and you just mentioned that it's boring in prod. Did you have a quiet week?
I did have a quiet week. Unfortunately, Rust doesn't solve all problems, so a few pages, but not too bad.
No Sev ones then.
No sad ones.
Cool. So how's it gone? We talk a lot about performance. Tell me about these graphs.
Yeah. So when we evolve our services, we will run the new service side by side with the old one to gain confidence in its results over time. So we'll typically have the new database shadow queries to the old one, and then we'll compare the results for correctness. As time goes on and we gain confidence, then we let the new system start to answer some actual production queries. So in this case, the REST database was already serving production traffic, and we were sending 50% of traffic to the old database and to the new one. And here we see that there was a sudden spike in incoming points. So we started ingesting much more data than we were ingesting before. And on the left, we see that as that ingestion spike happened, which is the top graph, on the bottom, we see that the service became overwhelmed and stopped answering queries. Then on the right, we see that the REST service, which was consuming exactly the same amount of data, was able to absorb it. And not only did it absorb the write load, it continued to reply to its own query load, and it even absorbed all of the queries that were going to the previous database. So it started answering 100% of queries while ingesting all of the data. And yeah, if you zoom in, you'll see that while the previous database peaked at 60K BPS per pod, the new database was able to do 60 times more and peaked at almost 4 million BPS per pod.
Cool. And the one other thing that jumps out at me is that I think there are less lines on the graph on the right, and I suspect that might be the instances of the service. Is that accurate too?
Yes, there were fewer pods on the new database than there were on the fewer pods on the new database than there were on the previous one.
So when you see this after you build a new service, it's pretty much as a resounding a success as you could hope for, I think, right?
Yeah, that's right. Yeah, very happy with it.
Cool. Thank you for that. That was really interesting.
Sure.
Let's jump over to Toby for a bit. Toby, you've been working on introducing Rust to the Datadog agent. Could you tell us a bit about the agent itself for folks who aren't working with Datadog at the moment?
Yeah. So the Datadog agent is the entry point to the Datadog platform, right? So customers run it on their servers, their Kubernetes clusters, their serverless environments, kind of anywhere where you might be running your workloads. Ideally, you try to meet you where you are. And the agent it's a piece of software, it's a process, it's an extension, it's something that runs alongside your application, and it shuttles telemetry data back to the Datadog platform. So that's custom metrics, logs, traces, OTLP. Some of it is data you send us or you send to the agent, and some of it is data that we kind of try to scrape from your environment on your behalf to figure out where you're running, pull metadata to enrich your data with. But ultimately, it's about getting the data you care about, that telemetry data about services you're running, whatever it is, back to the Datadog platform so you can do something with it, alert on it, graph it, log it in some way, shape, or form.
Cool. And how has the performance and feature set of the agent changed over the years?
It's changed a lot. So kind of like Duarte said, early on, internal services were Python, so was the agent. We moved to Go for internal services. We also moved to Go for the agent, keeping kind of everything in lockstep. And a lot of this is before my time, and we're talking 8 or 9 years ago. But originally, at least for the agent, certainly, a big part of it was performance. You're adding more features, and you started out doing very basic stuff, but you add more stuff. People are sending more data. Uh, we want to be more efficient with it, so move to Go. And over time, we've only ever added more features. Cloud environments and platform orchestration, technologies, just more and more things that the agent needs to handle, be able to understand, more data types. That's just, it puts a strain on the software that we ask you to run. It puts a strain on our own internal software, the services we use to power the platform. And so the performance needs and requirements have only ever gotten, you know, more important, more stringent over time as we certainly add more features to the agent, more features to our own platform, and that sort of thing.
Cool. So here too, our use of Rust or our recent introduction of Rust to the agent is driven by a similar desire to, on Duarte's side, a desire to optimize our resource usage for ourselves, and in this case also for our customers. Can you tell me a bit more about how we're planning on starting with Rust here? Where are we looking at introducing the agent to it initially?
Yeah. So our foray into Rust proper for the agent is in the form of a project called the Agent Data Plane. So if you imagine, again, the agent is a kind of a conduit for getting data from your applications to the Datadog platform. Um, but those data flows, those custom metrics, logs, traces, and so on, they're effectively unbounded user input, right? Like we don't know how much you're going to send us, and in some cases, maybe you don't even know how much you're going to send us. New applications get deployed or more traffic, whatever. Um, and those can put a strain on the current agent. Obviously you send more data, you might intuitively expect that you use more CPU or memory to process more data. You kind of really can't beat physics in that regard, but we can do better. We should be able to do better, be at least be more efficient about that, and not make it that it's you send twice the data and you have to use twice the memory or CPU. And so we wanted to try to figure out could we do those things in Rust. Rust in particular gives us the flexibility to be very precise about how we lay objects out in memory, avoiding, some of the typical like runtime overhead that you might pay in other languages like Go or Java or something. Um, and when it comes to unbounded user input, those are kind of exactly the places that you want to be as efficient as possible, because ultimately, again, we don't want customers to have to pay any more of a cost than they have to send us more data. Like it helps you get data there faster, or it helps you get us more data to like show you insights on. And if it means that like sending more data is going to, like, you get in that vicious cycle, it's like going to penalize you to be more successful, like that sucks. um and so we want that to be more efficient, and Rust is kind of a natural fit in that regard. And that's why we've started kind of poking around with this agent data plane project to see how much better we can do in that regard.
Cool. Can you give us a bit of an insight into, I suppose, the core design decisions that you were making as part of this workload?
Yeah. I think ultimately it boils down to that we want to focus on, I think, the arguably simpler problems. The agent does a lot of stuff today. Again, it handles all these custom metrics, logs, traces, what I would call like telemetry data flows. But it also does all that other stuff I mentioned. It's doing workload metadata. Where's your application running? Where is the agent running? Pulling information, things like remote configuration, talking to the Datadog platform, new advanced things that we have like eBPF based profiling, and or sorry, not profiling, like workload, cloud workload security, all these types of things. Um, but those some of those things in particular, the more like metadata, kind of low throughput, whatever, um, those can exist kind of fine by themselves. We really want to focus on um, you know the core telemetry data flows, and that is, again, it's very memory layout centric. It's very efficient processing, reusing memory, stuff like that, where we know we can amortize some costs over time because we have a very narrow focus on what we need to do. And so arguably, like a lot of the things that we're doing in Agent Data Plane, doing in Rust, like they aren't novel. Um, it's it almost sounds silly to say, but it's like the basics, right? Reusing memory, um, avoiding cloning and copying memory if you don't have to. And it's not that we can't do these things in Go; it's just that we can't do them easily in Go. And in some cases, like you're almost right on the cusp of like something being impossible, and like you're really contorting yourselves to do it in Go. It's possible, but like at what cost, right? But in Rust, some of these things are just there. You either get them for free or they're just natural. And so again, things like object pooling and pre-allocating buffers and just avoiding copies and being more stringent about like, how data comes into the system, how it moves through the system, and then how it leaves the system. It's just in some cases vastly simpler to do in Rust. And so a lot of what I do day to day is more about like how do we build this code base to make it easier for other developers on the agent in the future to start onboarding and not having to necessarily learn and care about all these, the minutia of how the data moves around. Think about it more like building blocks and primitives. Like I want to add a new feature. I have this like toolbox of things to grab from, and I know that they're done right because you know we did it once. Rust gives us the confidence that like when we wrote it and now test pass and it compiles and we've seen the performance benchmarks, like it's not going to like change out from under us, like those guarantees, those invariants. So that's mostly what I focus on day to day, at least now, is kind of like how do we make this simpler for people to get all these benefits without necessarily having to care about the kind of the minutia, I guess, right, of the underlying system.
Cool. And it sounds like it's a really similar sort of theme to what Duarte was talking about, that it's not rocket science. It's just that you're able to use the language in a way that lets you be a much more expressive with how you use the resources available to you.
Exactly. Again, like Rust is a systems programming language, which kind of like has this like baggage attached to it of like, twiddling the bits and being very precise. And like that's true. You can do those things, but I think ultimately like what it boils down to is that like it has a range of tools, a range of patterns, primitives, whatever you want to call them, that you can get that nitty-gritty if you want to, but you can also like continually like move up and down the stack to abuse a phrase here. Um, add the control where you need it. And so sometimes we're using the type system to do interesting things to make sure that like we can have multiple implementations of something without having to pay a performance penalty. Sometimes we are touching raw pointers. We're burgeoning into the unsafe area, but only where we really need to, and it stays there. And that's all we have to do. But ultimately, at the end of the day, yeah, it's about like focusing on your data model, like what matters, and only applying is the minimal amount of like very particular you know raw pointers or type system tricks or whatever to get what you need to do, and then no more. And that's just kind of like where it stops.
Cool. So how's it going?
uh I'm a little biased, but I would say it's going very well. So we've been, building this agent data plane, project, experiment, whatever you want to call it, for the past almost a year, a little over a year. We've been targeting handling custom metrics of DogStatsD, first because it's somewhat the simplest thing, even though there is a lot to it. But it's also the thing that powers people's dashboards and monitors in many cases. And so we've been very trying to move slow. We finally gotten to the point where we have it in just about 50% of our production internal environment. And we have some graphs here where in one particular cluster that's very, very high custom metrics workload, we saw like nearly a 25% CPU reduction over the core agent. The core agent is the process today that would otherwise handle custom metrics. And so you can see we've deployed ADP. It's a new process, or a sub agent as we would call it. And even with this new process, with all of its own kind of baseline overhead, all the memory and structures that it allocates and all that sort of stuff, um, these two processes together are still a net 25% reduction in CPU. And we have another slide where we can also see it's a net 33% reduction in RSS. So we're spending less CPU, less memory on the same exact workload, um, with something that we haven't tuned it to the hilt. There's a lot of stuff along the way, you get a little, "Oh, I'll make that better here," but we haven't gone particularly deep on trying to like optimize very narrowly, certainly not to our own workloads. It's a general purpose piece of software that's meant to work well whether you have a lot of metrics or a low amount of metrics. And so these are somewhat relative. Again, this is a cluster with a lot of metrics flowing through it. Not everyone's going to see these numbers, or you might see these numbers, but it might just mean that that percentage is a megabyte or two. But in this case, I think can't really see the numbers. They are on the graph; they're very small, but we're talking about hundreds of megabytes on average in this particular example that you see here that we're saving in memory, or whatever it was. I think like 100 millicores, something like that we're saving per pod. And like Duarte said, at our scale, these percentages can be particularly meaningful. This could be thousands of cores that you're saving or terabytes of memory that you're saving, depending on your workloads. And so, you know, and this is only one fraction, one portion of what the core agent in terms of core telemetry data flows that it handles is just metric, but there's also logs, there's traces, there's OTLP. These are all other data flows that some of them are actually heavier than custom metrics for a lot of customers, where we hope to ideally in the future be able to apply this same sort of pattern and ideally extract these same sort of benefits. And so, you know, we still have a little bit of a ways to go to make sure that we feel super comfortable with this being something that we want to release to customers, that it's not going to change anything for them. But so far, it's been going pretty well.
Yeah, I mean, a 33% reduction in RSS is probably nothing to sneeze at, even if the so, I mean, I look at your graphs and I ask myself, are we rewriting everything in Rust now? Is there a limit to the ambitions of the Rust team?
Well, so yeah, so right now this is purely doc.sd or custom metrics, whichever term as a customer you're most familiar with. Um, in the future, we're definitely looking at other telemetry data flows that we want to move over. Logs and traces are the most natural in those, right? Like kind of like the three pillars, right? Maybe not three pillars, the three typical things that people think of when they think of like data types for telemetry observability data. But there's also stuff like OTLP. It's kind of a separate protocol with its own signals and data model there. Um, in some cases, logs as an example, the current agent, the Go-based agent, does pretty well with them. Maybe in the future we want to move them over just for the sake of having them all be in one place in one project, done consistently. But we don't necessarily need to. Traces are, perhaps more important than that. But again, going back, some of the other stuff, right? Like we don't want to boil the ocean and try to rewrite the entire agent. There are a lot of things that it does well already. The code, even if like you're a person that dislikes Go and thinks it's, nowhere near as good as Rust, like a lot of this code is battle tested. It's run on millions of hosts. It's been used for millions, billions, trillions of invocations of serverless, functions or, whatever you want to call it. Um, and it just works. And so, workload metadata stuff, figuring out if we're in a Kubernetes cluster or we're running on a Roku or something, there's no need to change that. It's low volume, it's low resource consumption, it works well. We care about the things that are our user, unbounded user input. And we probably failed to mention it before, but another kind of core thing is that like we want to focus on trying to make things more deterministic. So things like metrics and logs and traces, those are the things that ideally are maybe going up because your business is more successful, you've got more customers, more traffic. We don't want that to be the thing that topples the agent. Things like scraping Kubernetes metadata or something like talking to your the IMDS service and ETs2, that's pretty low volume. It's already kind of deterministic. There's no reason to change it. It's just more code to write that you have to deal with. We want to focus on making things more deterministic, kind of tamping those unbounded user inputs, making sure we can process them as efficiently as possible and as consistently and deterministically as possible.
And that sounds very pragmatic to me, although I have trouble reconciling it with the rewrite everything in Rust slide before. But I mean, certainly, as you
I know.
said, the agent we've been extending it for years and years now. It doesn't seem super rational to go through and rewrite these kind of low volume paths, as you say. What lessons do you have for companies that are looking to adopt Rust in components that are being deployed to their customers? When does it make sense? When doesn't it make sense? Are there any kind of like high level learnings you can tease out of this experience?
Yeah. Um, I mean, so we're working on the agent data plane because we're thinking about, a data intensive application that needs to be highly reliable, right? Like custom metrics and things like logs and traces, right? These are things that are ultimately powering monitors, dashboards, things that people depend on for like their business operations day to day. Some people's business operations are flights. planes in the sky that, like you really want to make sure that they're doing the right thing. And some people it's, it's maybe just an e-commerce site or whatever. But ultimately at the end of the day, right, you're trying to take this telemetry data and turn it into something usable to see how your systems are doing, to maybe save money, to maybe make sure they're working. And so like high reliability is kind of, I think to me, the most important thing. There's a lot of ways we could have taken to, rewrite parts of the agent to make them more efficient. But ultimately, like it needs to work before it does anything else. That's the baseline. Like it has to work and it has to work right. And when we ship something out to a customer, we really want to make sure that it works right. And so if you have like like a system that you would classify as high reliability, something that like the data needs to make it there, it needs to make it there in the right shape, format, whatever, Rust is a natural choice. If it's data intensive, I think Rust is also a natural choice because it's not too much of a stretch to move from another language to Rust. It's fairly doable, and if you already have a problem that's kind of data intensive, then it might be worth moving over. So those are, they're kind of the obvious choices there. It's not too deep of a insight there, but I think focusing on what your problem is in particular is just good engineering practice in general. Um, and if you don't necessarily have those problems, you're talking about something low volume. It can be maybe things can be fallible. They don't have to always work right, and it's maybe more easy or maybe more important to get features out more quickly or something like that. Then maybe Rust doesn't make as much sense. As much as I love Rust, as much as Duarte loves Rust, right? Like writing stuff in Rust feels great. And if you have a greenfield project, by all means, go for it. If you've never used Rust before, it might take you a little longer. And then maybe we're talking about, does it matter to get something out quicker versus, later? But if you're already working on a project and it needs to be faster, it needs to be more reliable, then Rust is potentially worth it. Um, I don't think there's any particular pitfalls of Rust compared to any other language when it comes to things like rewriting or you know, platform support or whatever. The ecosystem is great. I think the tooling is great. Um, there's always going to be growing pains if you're starting out with a brand new language. That never changes, probably never will. Um, but everything around it that, you as a developer writing something in Rust would, potentially, or writing anything in any language would need to reach for, I think it's all there. Any of the older concerns about like, is the ecosystem there? Is the tooling there? Is it too slow to build? Like those have all kind of been washed away for the most part. And so again, I think it mostly just boils down to, at least for me, like do you have something that needs to be high reliability? Do you have something that's very data intensive? If you do, then I think Rust is a natural choice. But if you don't, then it's, I think, just, it's back to the basics, right? Like, do we really need to rewrite this in Rust? Do we have the time to rewrite it in Rust? Is it going to give us some benefits? Let us harmonize with existing code we have in Rust. If so, then maybe it's the right choice. If not, then, you know, choose how much you really want to rewrite something in Rust and go from there, I guess.
Cool, thanks. And with that very pragmatic footnote, that's all we have time for today. Thank you, everyone who has jumped on, particularly to the Premiere stream. I hope you learned something interesting about Rust, or at the very least about our adoption of it at Datadog. If you're hanging around in Premiere to the end, thank you for hanging around. Check out the other videos on our YouTube channel and enjoy the rest of your day or evening.